Hi, my name is Jahan, and today I'm going to show you how to use induction to prove that n cubed plus 5n is divisible by 6 for all n in the natural numbers. So here I have a skeleton for what all induction proofs should look like. This one is specifically for weak induction, but the inductive statement should be the same for both, and the inductive step should be the same for both, as well as the base case. But usually with strong induction, there's more base cases than one. In this case, there's just the one. So the way we're going to fill this out is let P of n be the statement that, now this first blank, we fill in with what is our proof. In this case, n cubed plus 5n is divisible by 6. Well, that's English. We need to write this in mathematical terms. So the way we would do that is n cubed plus 5n equals 6k, where k is an where k is an element of the integers. That is 6 times 1. That would be 6. 6 is divisible by 6. 12, 6 times 2, divisible by 6, and so forth. Okay, our next blank is we will show P of n holds for all. In this case, they don't give us a starting point, but they say for all n in the natural integers. So we're assuming n is greater than or equal to 0. And like I said before, we're going to be using weak induction for this particular problem. Okay, since we're saying for n is greater than or equal to 0, our base case should be the first case, which is n equals 0. The way we prove this is we just plug it in. Well, we said P of n is P, so in this case, P of 0 is the statement that n cubed, so in this case 0 cubed plus 5n, 5 times 0 equals 6k. Okay, is an element of the integers. So we can clearly see 0 cubed plus 5 times 0 is 0 equals 6k. So in this case, we just need to say k equals 0. And then we can rearrange the left side to say 6 times k equals 6 times k, because 6 times 0 is 0, and therefore a multiple of 6. So 0 is divisible by 6. So our base case works. Cool. Moving on, we have our inductive hypothesis. So this is where we set up our dominoes that we will then knock down in the inductive step. So assume P of k is true for some k is greater than or equal to, in this case, we're using 0 because that's our starting point. And that's all we have to do for our inductive hypothesis. Now our inductive step. This is where most of our math gets done. We've set up our dominoes for up to, or for P of k. We now want to knock down our next domino, which is P of k plus 1. And the reason I say dominoes is because if we say P of k knocks down P of k plus 1, or shows that P of k plus 1 is true, then we can then say that P of k plus 1 should also show P of k plus 2 is true by the same logic. And we can keep going on forever. So how are we going to show that P of k plus 1 holds? First, again, we plug it in. K plus 1 cubed. You know what? I'm going to replace this variable. Normally use k, but because I used k as the indicator of it being a multiple, I'm going to use a different variable here. Let's use x. So x plus 1 cubed plus 5x plus 1, plus 1 equals 6k. Okay, first step, let's look at it. Let's expand. X cubed plus 3x squared plus 3x plus 1 equals 5x plus 5. 5x plus 5 equal, okay. Now let's combine like terms. And here we go. Okay. The first thing we want to do is in some way use our assumption that P of x holds true. Well, P of x is the statement that x cubed plus 5x is a multiple of 6. So let's pull out an x cubed plus 5x from our left-hand side of this equation, and we'll get 3x squared plus 3x plus 6 left over. Well, using our inductive hypothesis, we can say that x cubed plus 5x is 6, let's say m, where m is some integer. And this is using the inductive hypothesis. Okay, if we want to show that the left-hand side of the equation is a multiple of 6, we need to show that the rest of this is a multiple of 6, because we've already found that one part of it is, and if we add two multiples of 6 together, we'll get another multiple of 6. So how can we show that this is a multiple of 6? Well, first we can take this plus 6 and just move it over. So 6m plus 6 plus 3x squared plus 3x equals 6k. So shortened it even more. Now we just need to prove 3x squared plus 3x is a multiple of 6, because obviously 6m is a multiple of 6. Add 6 to it, it's still going to be a multiple of 6. How can we prove 3x squared plus 3x is a multiple of 6? Well, one way to do this is to say that a multiple of 6 just means that the number is divisible by both 3 and 2. We can clearly see here that 3x squared plus 3x is a multiple of 3. By factoring out this 3, we get x squared plus x, right? So we know that this is a multiple of 3, so we just need to prove that x squared plus x is a multiple of 2. We actually already know that this is a multiple of 2. We can do a separate proof on another time, but logically, x squared plus x factors to x, I'll write it over here. X squared plus x factors to x times x plus 1. These are two consecutive integers being multiplied together. By definition, x must either be even or odd. If x is even, then this product must also be even. And if x is odd, then x plus 1 must be even, again making this product even. So in either case, this product must be even. Therefore, in any case, x squared plus x must be a multiple of 2. So let's call this a multiple of 2. So what variable do we want to use? We've already used m. Uh, let's say p. Okay, so we're saying that this is 2p, because an even number can just be rewritten as 2 times an integer. So we must specify p is an integer. Now we have 6m plus 6 plus 6p equals 6k, where m and p are both integers and k is also an integer. We can now factor out this 6, leaving m plus 1 plus p on the left side and 6k on the right side. 1 is an integer, and m and p are both integers by definition, here and here. So that means that m plus 1 plus p must also be an integer. And we can just rewrite let k equal m plus 1 plus p, and we know that these are both integers by definition. So we just get 6k equals 6k, which is always a true statement. So basically, what we've proved here is that the left side of our equation is a multiple of 6. At every line in this in this column, the left side of the equation is a multiple of 6. Going all the way back up to the top row, which is p of x plus 1. So we've done it. We've finished. We've concluded our inductive step. And the final piece of our inductive proof here is to just formalize our conclusion. This is once again a formula that can be put inside your skeleton. You always start it with we have shown P of P of n holds for all n in the natural numbers. And let's rewrite that in its full form, which is that is n cubed plus 5n is divisible by 6. Thank you.